What makes your smartphone smart or your computer a chess master? The answer: microchips. These tiny silicon squares are the brains behind almost everything we use today. A single microchip, often smaller than your fingernail, can contain billions of microscopic switches called transistors, the building blocks of all digital electronics. The precision required to create these chips is astounding, involving extreme heat, powerful chemicals, and clean rooms cleaner than a hospital operating room. Let's embark on this amazing adventure to see how a humble grain of sand becomes the silicon brain that powers your world. Our journey begins with something as simple and familiar as sand, the kind you find on beaches all over the world. Most of this sand is made up of tiny grains of silicon dioxide or SiO2, a mineral that's both abundant and essential to modern technology. While silicon is one of the most common elements on Earth and relatively inexpensive, the silicon used in microchips must be incredibly pure, refined to an astonishing 99.9999999% purity. Even the tiniest impurity can disrupt the performance of a microchip. To achieve this, the raw silicon dioxide is heated in massive industrial furnaces to temperatures exceeding 2000 degrees Celsius. This intense heat separates the oxygen from the silicon, leaving behind what's known as metallurgical-grade silicon, a crucial first step in the transformation. But that's not pure enough for electronics. The silicon is then subjected to further chemical purification, transforming it into electronic-grade polysilicon, which is almost entirely free of contaminants. Next comes the Czochralski process, a remarkable method where the purified polysilicon is melted in a crucible. A tiny seed crystal is carefully dipped into the molten silicon and slowly pulled upward, rotating as it rises. This process forms a large, flawless cylindrical crystal called an ingot. The resulting crystal has a perfectly ordered atomic structure which is absolutely vital for building reliable and efficient transistors, the building blocks of all modern electronics. The ingot is then ground to a precise, uniform diameter and carefully sliced into ultra-thin wafers using a diamond-tipped saw. Each wafer must be perfectly flat, and even to ensure proper chip fabrication, these wafers, often less than a millimeter thick, are polished to a flawless, mirror-like finish by robotic arms. This smoothness is essential, as even microscopic scratches could ruin the delicate circuits that will be built on them. From humble grains of sand, we've engineered pristine silicon canvases, each one ready to become the foundation for the powerful microchips that drive our computers, smartphones, and countless other devices. The transformation from beach sand to perfect crystal is nothing short of extraordinary. We begin with polished silicon wafers, the ultra-flat, mirror-like discs that serve as the foundation for every microchip. These wafers are carefully prepared in ultra-clean environments, ensuring that even the tiniest speck of dust won't interfere with the intricate process ahead. With these pristine wafers, we start building circuits that will power everything from smartphones to supercomputers. The next step is photolithography, a process that's often described as printing with light. This technique is at the heart of modern chip making, enabling us to etch incredibly detailed patterns onto the wafer's surface. First, the wafer is coated with a thin layer of light-sensitive photoresist. This is done in a spotless clean room where technicians wear special suits to prevent contamination. The photoresist acts like photographic film, ready to capture the circuit's blueprint. A mask containing the intricate circuit design is carefully aligned above the wafer. Ultraviolet light is then projected through the mask, transferring the pattern onto the photoresist below with astonishing accuracy. Where the light hits, a chemical reaction occurs in the photoresist, causing it to harden or dissolve, depending on the type used. This creates a precise, stencil-like pattern that will guide the next steps of chip fabrication. This photolithography process is repeated over and over, layer by layer, each time adding new features and complexity. Gradually, a three-dimensional structure emerges, with hundreds of layers stacked to form the final microchip. The level of precision is truly mind-blowing. The features etched onto the wafer are measured in nanometers, thousands of times smaller than a human hair, allowing billions of transistors to fit on a single chip. It's a delicate dance of light, chemistry, and engineering, transforming a blank silicon canvas into an intricate electronic city, a marvel of modern technology that powers our digital world. With the photoresist pattern in place, we etch the exposed silicon wafer, removing layers to form circuit pathways. Doping introduces impurities to change silicon's electrical properties, creating N-type and P-type regions for transistors. Ion implantation embeds impurity ions into the crystal lattice. The process repeats, depositing new materials, applying photoresist, and using photolithography to create new patterns. Insulating layers prevent short circuits, and metal layers form the wires connecting transistors. Each layer aligns perfectly, building complexity from simplicity. It's a magical process that constructs a microscopic city. After building all the intricate layers, the silicon wafer, now densely packed with thousands of microchips, undergoes a rigorous testing process. Robotic probes carefully touch each chip, checking for even the tiniest flaws or imperfections that could affect performance. Any defective chips are meticulously marked and set aside, ensuring only the highest quality make it through. The good chips are then precisely sliced from the wafer into individual dies, each one a marvel of engineering, before being packaged for protection and transport. These fragile silicon dies are carefully mounted onto lead frames, then connected with ultra-fine gold wires in a process called wire bonding. Finally, they're sealed inside tough, black plastic casings to shield them from damage and contamination. From humble grains of sand to the creation of a silicon brain, this manufacturing journey is nothing short of extraordinary. It's a story of relentless innovation, where science and engineering come together to push the boundaries of what's possible. These microchips are the silent powerhouses inside our smartphones, medical devices, and even satellites, enabling communication, healthcare breakthroughs, and space exploration. They are the foundation of the digital revolution, transforming our world. Engineers and scientists around the globe are constantly striving to make chips even smaller, faster, and more energy efficient. They experiment with new materials and architectures, always searching for the next leap in performance and capability. The microchips of tomorrow will power artificial intelligence, drive autonomous vehicles, and help solve some of humanity's greatest challenges, from climate change to disease. So next time you use your favorite device, take a moment to appreciate the incredible science, precision, and ingenuity inside. Each chip is not just a piece of technology, it's a small, powerful piece of our future.